So we continue talking about the limits of the sequences, and another familiar theorem that we face here is the squeeze theorem. So suppose that I have a sequence an that's a squeeze between bn and cn for all n. So an is bigger than bn but less than c sub n. And if I know that the limit when n goes to infinity of bn is equal to the limit when n goes to infinity of of cn is equal to some letter L, then I can conclude that the limit of an when n approaches infinity is equal to L, since this will be squeezed between these two values. Okay. Some examples and about the use of this theorem. Consider the following sequence, which is defined by cosine of 3n minus n squared over n squared. Now, first, the main problem is that doesn't allow us to just find the limit here directly is because the cosine of whatever here you have inside, like 3n minus n squared, approaches negative infinity. But the cosine of infinity or cosine at plus or minus infinity does not exist, since the function of cosine keeps oscillating and does not approach a single value at when n is really large. And actually it keeps oscillating between -1 and 1. So we know that cosine of 3n minus n squared is always between -1 and 1. I don't care what's inside the cosine, but the cosine and the sine function are always squeezed here. Now, because n squared is a positive number, so I can divide by n squared. So then, -1 over n squared is less than or equal to cosine 3n minus n squared over n squared, less than or equal to 1 over n squared. Now, I know that the limit of -1 over n squared, when n approaches infinity, this goes to 0. And 1 over n squared, also when n goes to infinity, this goes to 0. So you can see here that the limit of cosine of 3n minus n squared over n squared when n approaches infinity is squeezed between 0 and 0. So by the squeeze theorem, that limit is equal to 0. Okay? So we conclude that this approaches 0 as n goes to infinity. So clearly this is a convergent sequence. Another example, b sub n equal -1 over 2 to the power n. Again, here we have to be very careful, and I will talk more about the limits of this type. This is called like a geometric series or geometric sequence. I'll give you some result at the end, but here I wanted to think about it in this way. First, you cannot really transform this, okay, into f of x equal -1/2 to the power x. Okay, so this is not possible in our case. The reason I cannot do this transformation and use the theorem that I mentioned before is because when we defined exponential functions, always the base is positive. The base was never negative. So here, this function does not exist. So what do we do in this case? Well, I know that b sub n is equal to -1 to the power n over 2 to the power n. I mean, I can use the properties of exponent to write it in this way. So we can see the following here, that the top, which is -1 to the power n, is either between, could be either -1 or 1. So as a result, I know that -1 to the power n is squeezed between these two values. Okay, then I can try to use the squeeze theorem here. So I have -1 over 2 to the n. Again, I don't worry about changing the signs here because I'm dividing by a positive quantity. Okay. Now, this is something I know how to find, okay, because I know that this is like -1 over 2 to the x. So this has the form of -1 over infinity, which goes to 0, when n goes to infinity. Similarly, this goes to 0 when n goes to infinity. So by the squeeze theorem, I can conclude that limit of b sub n when n approaches infinity is equal to 0. So the sequence is convergent. Here's also a nice theorem that's very easy to prove if we apply the squeeze theorem. So we are saying the following, that if the limit of absolute value of a sub n is equal to 0, then the limit of a n when n goes to infinity is 0. The reason is very simple here. We know that a n is less than or equal to absolute value of a n and greater or equal to negative absolute value of a n. Any number has this property, because if the number is positive, then it's going to be the upper bound. If the number is negative, then it's going to be the lower bound. So it's always between these two values. Okay. Now, because we know here from the given, so in the given it says that the limit of absolute value of a n when n approaches infinity is 0. So I know that this is going to go to 0. This is also going to go to actually negative 0, which is 0. So by the squeeze theorem, so then I can conclude then by the squeeze theorem, I can conclude that limit of a n when n goes to infinity is equal to 0, and the theorem is proved. Okay. Here's the direct application about this problem, or about the theorem. Suppose that I want to find the limit when n approaches infinity of negative 1 to the power n over n. So there is no need to say, well, you know, negative 1 to the n is between negative 1 and 1, divide by n and apply what I did for negative 1 over 2 to the power n, which is not too bad. But I think here it's shorter if we just think about this as a n. Okay, absolute value of a n in this case is actually absolute value of negative 1 to the power n over n. Now I know that n is positive, so absolute value of n is n. And I know that minus 1 to the power n, this is either 1 or minus 1. So when I take the absolute value, either ways, I'm going to get 1. Okay, so absolute value of an is equal to 1 over n, since limit of absolute value of an when n approaches infinity is equal to the limit when n goes to infinity of 1 over n is equal to 0. Then by the theorem above, I can conclude that limit of an when n goes to infinity is equal to 0, which means that limit of minus 1 to the power n over n when n goes to infinity is equal to 0. Now, you cannot apply this, so caution here, it's very important that, so caution, it's very important to note if, let's say, limit when n goes to infinity of an is equal to L, okay, this does not imply that limit of an is equal to L or plus or minus L. Okay, so you have to be very careful. You can only apply this theorem if you know that the limit when you take the absolute value is actually 0. Okay, otherwise it doesn't work. Now this is also a theorem that you may have seen something similar before when you take the limits for functions, but it will also be applicable for sequences. Suppose that I have a function f that's continuous at x equal a, and an is a sequence which converges. So here you can see clearly that I have a typo. So this is infinity here, and this is infinity. So limit when n approaches infinity of f of an. Now, so I know two things. I know that f is continuous, and I know that limit of an when n goes to infinity is equal to some letter a, finite number. So the limit of the function of an is the same as the function of the limit. So this property from here to here, this is used due to the continuity of the function f. And then the answer will be f of a. So a direct application for this one is the following. We know that the limit of an, if we think about this an, that's equal to 1 over n, when n approaches infinity is 0. And I know that the function f of x equal cosine x is continuous everywhere. So in particular, it's continuous at 0. So then, limit when n goes to infinity of cosine of 1 over n is cosine of the limit. That means this is like, what we are trying to say here is that if you want to find the limit of cosine of 1 over n, so informally we are doing the following. This is like cosine of 1 over, you can just apply, I mean, this has the following form. This is like cosine of 1 over infinity, so this is like cosine of 0, which is 1. Okay, but it must be written in this way because this is the proper way to write it. But informally, this is what we are really saying, and this is what we are really doing in terms of functions, and the same thing we do here for sequences. Okay, here this is just a review on how you compute the limit when you have like a rational function. So remember that if you have a rational function, it's easy to compute the limit. We only care about the leading term on the numerator and in the denominator. So for example, if you look at this one, here, the leading term is 2n squared. Over here, the leading term is n squared. Okay. Now here I'm trying to show you exactly what we do, but you can use this as a formula. Okay, so my answer is going to be 2. Where the 2 comes from? 2n squared over n squared. Now, if the degree on the top is higher, then you get infinity. If the degree in the bottom is higher, then I get 0. Okay, but in general, this limit is done in this way. That's the limit when n goes to infinity. What we do here is you factor out the greatest common factor. The greatest exponent. So you factor out n squared. You end up with 2 minus 1 over n squared here. Then you factor out n squared in the bottom. You end up with 1 plus 3 over n, because there's one n that will cancel. Now n squared cancels with n squared, so this gives you 2 minus, when n goes to infinity, this guy goes to 0, over 1 plus 0, which is 2, as you can see on the top. If the degree of the top was, for example, 4, then I'm still going to have an n on the top, and my answer will be infinity. If the degree on the bottom was n4 and the top was n squared, then I'm going to have an n squared left in the bottom, so I'm going to have 2 over infinity, which is 0. Okay, so you can do it like this, and if you just use the this result, then that would be fine. Now, this is a really nice example and a very important property that we'll see in this chapter, and also when we talk about series. Now, I'm just providing here the proof for completion, but I'm going to give you a much nicer proof when we start talking about series, a one-line proof. Okay, so for now, I just need you to understand one thing, that when I talk about factorial, remember the factorial is this. When I say n factorial, this means n times n minus 1 times n minus 2, and you keep multiplying till you reach 3 times 2 times 1. So for example, 4 factorial is just 4 multiplied by 3 multiplied by 2 multiplied by 1, okay, which is 24. 5 factorial is 5 times 4 times 3 times 2 times 1, okay, and then you can find the answer. But just note one thing here, that 5 factorial can also be written as 5 times 4 factorial. Okay, so this is a really nice property about factorials, and you're going to see lots of these functions, especially when we talk about series. So I want you to see two things here. First, I want to see that the definition of the factorial, and then the factorial function grows very fast. Also, the exponential function grows very fast. So which one grows faster? That's a good question here. Now the thing is, you cannot, for example, if you want to take that limit, okay, you cannot think of trying to make this as a function. Okay, because if you want to make this as a function, that's going to be like if you change the letter x here to some letter a, for example, that's going to be a to the power x over x factorial. But the function x factorial does not exist. Okay, this is only defined if the input is an integer, which is not the case if you just take f of x equal x factorial. So you can't consider this as a function and take the derivative or apply L'Hopital's rule here. So this needs more uh, details. So here we split the problem into two cases. I recommend that you take a look at these at the proof that's provided here. But as I said, I'm going to give you a better proof later. But what I want from you here is to understand something, that no matter what x is, okay, limit of x to the power n over n factorial is equal to 0. That means n factorial beats exponential. N factorial reaches infinity before exponential or any other exponential function can reach infinity. Okay, so this is the continuation of the proof. It's a bit hard, but not hard. I mean, you can take a look at these details, but it's a nice one. Here are some examples that I recommend you try. Okay, for example, here I can give you quick answers, and this depends on the examples that we mentioned earlier for rational functions. This goes to 1/2 because they have the same degree. So this is 1 times n, this is 2n, everything's good. This goes to infinity because the degree of the top is higher and the degree in the bottom is 1, the one on the top is 2. This goes to 1/2. Same reason as the first one. Okay, now what about that one? First, this can be done in the following way. You can use L'Hopital's rule if you want, but I don't think that I really need it here. I can do the following. That's limit when n goes to infinity. The same trick I used when I factor out the factor with the highest exponent for rational functions. I can factor out 2 to the power n. So this means 1 plus 1 over 2 to the power n. In the bottom, I can factor out 2 to the power n as well. So that's 1 over 2 to the power n minus 1. So 2 to the n cancel with 2 to the n. Now I can take the limit. The top will be 1 plus. Now 2 to the n goes to infinity. So 1 over 2 to the n is 0. So the top is 1 plus 0 and the bottom is 0 minus 1. So my answer is minus 1. Okay? Which means it's convergent. Now you can try that one. Verify that this is going to be equal to 0 and that's going to be convergent as well. So all these are convergent except this one is divergent. Here's another example where you can see the following. Limit has e to the n plus 1 on the top and 1 minus 2 to the n in the bottom. Again, you want to use L'Hopital's rule, you still need to be very careful. But what we can do is, like I did in the previous example, that's the limit when n approaches infinity. I factor out e to the n from the top. I end up with 1 plus 1 over e to the n. I factor out 2 to the n. I end up with 1 over 2 to the n minus 1. Now, that's the limit when n goes to infinity. You see I cannot cancel here. But what I can do is I can write this as e over 2 to the power n. Okay, this is 1 plus 1 over the n. This is 1 over 2 to the n minus 1. Now let's analyze the limit of each one of them. I know that the limit of the product is the product of the limit. So this guy, what happens to this when n goes to infinity? Well, I know that e is 2.7 something. So e over 2 is bigger than 1 because e is bigger than 2. And if e over 2 is bigger than 1, so this is like an exponential function where the base is bigger than 1. In that case, the function, let's say b to the x, when b is bigger than 1, is going to go to infinity as x goes to infinity. Using this idea here, that means this exponential function will, and which corresponds to that sequence, will go to infinity. This one is going to go to 1 plus 0 over 0 minus 1. So my answer actually is going to be infinity multiplied by minus 1, which is minus infinity. So the limit is does not I mean it's negative infinity, it's not finite, so the sequence is divergent. Here's another example. Limit of n squared over 1.01 to the power n. I'll tell you one thing. Always, okay, so you can think about it in this way, that you have polynomial is less than exponential, and this is less than factorial. Okay, that means when I look at that one, I will expect a 0 in my answer. The reason is the bottom one, of course, here exponential with base bigger than 1. Okay, I will expect okay, so this is an exponential function, the top is polynomial, I will expect a 0. But to prove this, you can use the L'Hopital's rule. Okay, so for example, that's like limit when x goes to infinity, x squared over 1.01 to the power x. Apply L'Hopital rules twice. That's the limit of 2x over 1.01 to the power x multiplied by ln of 1.01 when x goes to infinity. And then apply L'Hopital's rule one more time. That's the limit when x goes to infinity, 2 over 1.01 to the power x multiplied by ln of 1.01 times ln of 1.01. These are some numbers. Okay. Actually, these numbers are positive, but I don't care whether they are positive or negative because they're going to be multiplied by infinity. So this is going to be like 2 over infinity. Plus minus infinity doesn't matter, which is going to be 0. Okay. And here's you see here now when I look at that one, okay, then I'm going to say my answer will be 0. The reason is the example that I showed you, and I said you can use that result. Limit of x to the power n over n factorial is equal to 0 when n goes to infinity. So the factorial beats the exponential, even if it was 1000 to the power n. Now, of course, now if you try to plug in n equal 1, 2, 3, 4, maybe the first 100 values is going to give you that, no, well, 1000 to the power n is much bigger than n factorial. But then at some point, things will change and n factorial is going to beat it. So, and remember, when I defined the limit, I said when n is sufficiently large. When I say sufficiently large, that means it's very large, very close to infinity. Now here's an example that I'll show you the solution to, and this really shows you how we deal with factorials sometimes, the algebra of factorials. I need you to notice one thing, that n plus 1 factorial, which is n plus 1 multiplied by n, so again, use the definition. This can be written as n plus 1 times what's remained is n factorial. Okay, so we're going to use this property here. So the first thing we're going to do, we're going to split the fraction. So that's the limit when n goes to infinity, n factorial over this, plus limit when n goes to infinity, 1 over n plus 1 factorial. Now here, if you write n plus 1 factorial as n plus 1 times n factorial, then you're going to cancel the n factorial and you're going to end up with limit of 1 over n plus 1. So this becomes this. And we simplified using that rule. And this one stays the same. Now, this guy goes to 0 when n goes to infinity because it has the form 1 over infinity. Similarly, this goes to 0, so the limit will be just 0.